Hello and welcome to this brief video on logic. So, we're spending a lot of time in the beginning of your math class, your high school education, explaining to you what logic is and how we deal with it and what's mathematical logic, because that's where all this comes from. The basis of math is logic. The basis of math actually goes back to more the philosophy of the universe. People started working with math, especially the higher forms of math, not necessarily because that they wanted to count up the number of pigs in their yard, but what they really wanted to do was figure out the philosophy of the world and what truth is in it and what truth isn't in it. For a long time, mathematics have been seen more as a philosophy. It isn't until recently that we've seen it more as a computational type of art, which isn't what it really is. Math is about being able to learn how to think in a logical way. It's not so much about adding a couple numbers together. So here's one mathematician's think or feel on what math is. He says, mathematics directs the flow of the universe. It lurks behind its shapes and curves and holds the reins of everything from tiny atoms to the biggest stars. And he's not alone in this. Philosophers, filmmakers, logicians throughout history have always atoned math to something bigger than themselves, something universal. Coppola said that film is one of the three universal languages. The other two are mathematics and music. From the man who loves film, he's putting it right up there with math and music. Or that what's great is that because math is such a universal language, really our fans come in all shapes, sizes, ages, genders, race, and backgrounds and cultures. Math transcends anything that we might have prejudices in because of the logic behind it. It's this logic that makes people think that God uses beautiful math in the creation of the world, or the laws of nature are but mathematical thoughts of God, or biologists think they're biochemists, and biochemists think they're physical chemists. Physical chemists think they're physicists, and physicists think they're gods. Joke, by the way. And gods think that they're mathematicians. In general, mathematics was a way of narrowing down what's true and not. In science, we do a lot of hypotheses. We do a lot of changing. That's why science changes constantly. We know one thing, we learn something new, it completely changes how we see. Science thought the world was flat, and the world now isn't flat. We think that the universe is such and such. This universe probably isn't such and such. The more information you get in science, the more it changes. Math doesn't change. Math says this is either true or not, and we're only going to deal with it if it's true. Math uses a way of thinking to make something called a proof. Now, proofs are how mathematicians talk to each other and say, I know this is true, and it is true because of this. We're very much like crime solvers, where every little dot has to follow the next. Otherwise, you can't count it as a truth or a mathematical truth. You can do mathematical truths wrong, and your other mathematicians will find you along those lines and say, no, 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 that's not a true value. That's not part of math. You didn't prove it to 100%. Mathematicians don't take anything for granted. They start at the very, very beginning. So something as simple as 1 plus 1 is 2. Well, that's intuitive to us. 1 and 1, you have 2. 1 grape, 1 apple, you have 2 pieces of fruit. It's something that we take for granted as a population. But as a mathematician, you never can take this for granted. There were these two wonderful guys, Alfred Whitehead and Bertrand Russell, who actually proved without a doubt, that 1 plus 1 is 2. Until these guys proved it, without a doubt, it wasn't allowed to be used in a mathematical proof. Once you prove something's true, everyone can use it and we'll start from there. But if we don't know 100% that it's true, well, then it can't be used. In fact, these guys took 300 pages to prove the simple thought process of 1 plus 1 equals 2. Now, a lot of those 300 pages were really defining what is 1, what is plus, what is 1, what is equal, what is 2. But it really did take 300 pages for a mathematician without a doubt to say that this is truth. Now, you guys are at the very beginning of your little truth dialogue in how to form these type of things. And to start with, we really have to think about, okay, well, what is logic? How can we decide if something's true or not true? Well, the beginning of that is just verifying the truth of a statement. Statements have to be verifiable. In order for us to use them in math, it has to be something that we can say is true or not true. So I have a puppy. Well, that's true or not true. So I can use that statement. Now I have to verify it's true before it becomes mathematical like law, but just the statement itself, I have a puppy, is verifiable, so I can play with it. Or the sky is purple, my teacher is nice. There's a little problem with my teacher is nice because we have to define what is nice. But it's still something that we can define, so we can still verify it. I am 5'9" tall, or Timmy is silly. Same thing there. You have to really say what is silly, what does this mean? But they're still verifiable statements. Now, there's other things in our language that are not statements. They're not verifiable, and they can never be part of mathematical law. Something like close the door. That's a command. That doesn't have a true or not true. That's telling somebody to do something. Or the hat. Well, that's not an incomplete thought. Though that's an incomplete thought. That's like, if I said the hat is red, I can verify that, but I can't verify the hat. I can verify I have a hat or there is a hat, but I can't verify the hat. Or something else is not verifiable as a question. What is color? What is green? Those are a way of us for grabbing information, but they can't be verified. There's not a true or not true to a question. Okay, so there's also different types of truth values. We can have a truth value of something like, my mom's name is Debbie, which is different for every person. For me, this is true, but if your mom's name is not Debbie, this is not true for you. So it can have a different truth value depending on the different people. You can also have something like, the sky is clear today. Well, this is true or not true based on what day it is. So the day that I'm recording this, it's true. But tomorrow, it might be false. And when tomorrow becomes today, then that makes the truth value change. So it's changing based on the time period. Then there's other truths. Like we just saw with the last two guys, 1 plus 1 is true. That is a universal truth. We universally know that no matter what you do, 1 plus 1 is always 2. Or 4 divided by 2 is always 2. Another universal truth. These are true all the time, and these are the truths that mathematicians want to work in. They work in universal truths. And we'll find more about those as we go deeper into chapter 10 of our book. But for now, these little guys are more like, let's just begin by saying, is it true or not true? Now, once you find out something's true, you can use both of those truths to form another truth. So if I know 1 plus 1 is 2, which means they're the same thing, and 4 divided by 2 is 2, which means those are also the same thing, since 2 is in both of those statements, I can verify without doubt that 1 plus 1 equals 4 divided by 2. They're true, dependent on the first two truth values. This is a lot of what we're going to be doing. We know this is true. We know this is true. Therefore, we will get that this is true. Now, in the next little series, we're going to go over like how we know this and how we do this and how we set it up. But for now, I just wanted to leave you with a little thought. So, mathematical truths prefer simple words since the language of truth is itself simple.